All right, so let's talk about maps. Okay, so in their structure, there's a map structure. A map is a container object that stores a collection of key and value pairs. It enables fast retrieval, deletion, and updating of the pair through the key. So a map stores the values along with the keys. So before we learn, we pretty much store all the values, right? Now with the map, there's a key too. So the keys are just like indexes or like the room number, right? Those are the key. And then you can get the values inside, right? Corresponding to the key, like your student ID, and then you get your name, your grade, and so on. So that's just like a key. So in the list, the indexes are integers. In map, the keys can be any object, right? So it's not just an integer. It's just like the list, right? So a map cannot contain duplicate keys. Each key maps to one value. A key and its corresponding value form an entry stored in a map. So example, we have this is called a map, and this is a key, right? This is an entry. The entry has the element's value that's corresponding to the key, right? Like this is a search key and return John, like I said, that like ID and get the name of the person that's corresponding to it back. Like this is social security number is the key, right? Now we have hash map, linked hash map, and tree map, right? There are three types of maps. So let's look at the interfaces. So we have a map interface. This is an interface, and then sorted map. This is interfaces, and navigable map. Now we have an abstract classes called abstract map, and we have a concrete classes. Concrete classes, those are hash map that extends from abstract map, and linked hash map that extends from hash map. And we have tree map that extends from abstract map and implements the interface name navigable map. So this is just an interface of the map. We have key and the value, right? So the interface pretty much just provide the method for querying, updating, and obtaining a collection of values and a set of keys. Like we have get, provide key, and this returns the values. Key is an object. We can do put key to values, right? We can put all, like put more than one, remove by the key, and so on, right? So that's pretty much just helping, just like this structure. So you can see the generics pretty much just, this is for the entries. We have key and the values, right? Get key, get value, and set values. So this is for an entry interface, right? So the map interface, pretty much these are the methods that we have. Like in hash map, we have map and make sure it's going to be a key, right? Type, the value types, right? And we have linked list version of that hash map, right? So we call linked hash map. And the other way we look at sorted map. Sorted map pretty much just we have a comparator, right? So when you insert, it has to be sorted Like tree pretty much need that. Like we have to know, like we talk about the tree, right? Structure to the left, to the right, greater than, less than. So that's why we need that. Okay, and navigable map. You can go to like floor the key, ceiling the key, right? Lower the key, higher the key, pull first entry and pull last entry. So just be able to navigate right through the key. Alright, so this is just a test program. This is just use the Java library for map. So the key is a string, return the age integers like Smith age 30, Anderson age 31, and so on. So you put this into the hash map. Right, so this is called an interface map. We use hash map. Alright, so this is called, we create a tree map from a hash map that we created earlier through a constructor. Okay, now since we use tree map, then it's technically the benefit of tree map is going to make it like in order, right? Because they have comparable or comparator that we see in the interfaces earlier. Okay. So when we print, let's see the program here, right? So with hash map, when we print, it's not sorted, but when we do tree, it's sorted by the key, right? Anderson, Cook, Lewis, Smith. And this is just the linked hash map version. So now when we create that in the constructor, we have, this is called the factor, load factor, right? You initialize the capacity, we have a load factor. So we have load factor because of what this is dynamically increasing, right? So that's why this is pretty much just at 75%, that it's going to expanding, right? And this pretty much just created from, we added Smith, Anderson, Lewis, and Cook. So it's going to be in order like the way that we add. So those are three types of maps. Okay. So that's pretty much maps. So now the question that we know in the object class pretty much just the parent of all the classes or the great ancestors. So we have the equals. We know like string, we have dot equals, going to returns what? True or false if that equals, like compare like object by the attributes, right? And we also have Hashcode, returns a Hashcode value for the object. So this method is supported for the benefit of hash tables. So when we in a table, like we just see hash map, right? So that's a general contract of Hashcode. Whenever it is invoked on the same object more than once during an execution of Java application, the Hashcode method must consistently return the same integer, provided no information used in equals comparison on the object it's modified. So this integer need not remain consistent from one execution of an application to another execution of the same application. So you see that when we do Hashcode, it's return a Hashcode value of the object. Again, that's Hashcode used for the benefit of when you store that object into the hash, right, tables by hash map, right? But whenever you're dealing with this, there's a contract. if two objects are equal according to equals method, then calling the hashcode method on each of the two objects must produce the same integer result because it refers to the same object, correct? If it's not required, if two objects are unequal according to the equals method, then calling the hashcode method on each of the two objects must produce distinct integer results. Right? If it's not required that two objects are unequal according to the equals. However, the programmer should be aware that producing distinct integer result for unequal object may improve the performance of hash tables. So the key thing is efficiency, right? Let's read this one more time. Whenever it is invoked on the same object more than once during an execution of a Java application, the hashcode method must consistently return the same integer because it's the same object, provided no information used in equals comparison on the object is modified. The integer need not remain consistent from one execution of an application to another execution of the same application. Yeah, the number doesn't have to be the same because that's different application, right? So as much as is reasonably practical, the hashcode method defined by class object does not return distinct integers for distinct objects. This is typically implemented by converting the internal address of the object into an integer. But this implementation technique is not required by the Java programming language. Alright, so let's look at the question that you're going to get something like, what's the relationship between hashcode and equals method in Java? So the problem you will have is with collections where unicity of element is calculated according to both equals and hashcode. For instance, keys in a hash map. As its name implies, it relies on hash tables, and hash buckets are a function of the object's hash code. If you have two objects which are equals but have different hash codes, you lose. The part of the context here which is important, right? That's why objects which are equals must have the same hash code. That makes sense? So this is the contract that we were talking about, right? The contract is when you override equals method in Java, you should override hashcode method too. Then you always guarantee that what you're gonna get the same hashcode back for efficiency, right? Okay.
So is hashcode a key that's given to an object once it's executed, or?
So the question is hashcode the key that given to the object?
Yeah.
Hashcode is pretty much here, right? Go back to it's going to return a hashcode value of the object. This method support to be hashcode is it's pretty much just somewhere say it's just get the address, right? Here, right? Typically implemented by converting the internal address of the object into an integer. Right, the hashcode method defined by class objects. Right. It's going to return distinct integers for distinct object, right? That convert the internal address. Okay. So technically, whenever you overwrite, remember we overwrite equals, right? When we do comparison, right? So you should overwrite hashcode too. Okay. That's the contract that you may see the question like that. Okay. Let's see what this guy's. According to the doc, the default implementation of hashcode will return some integer that differ from every object. As much as is reasonably practical, the hashcode method defined by class object. This is exactly what we just read, right? However, sometimes you want to the hashcode to be the same for different objects that have the same meaning, for example. This kind of problem will be occur if you use a hash data structure in the collection frameworks such as hash table, hash set. Especially with collections such as hash set, you will end up having duplicate elements and violate the set contract. So let's try. Let's write some code and see. So actually, I have an example of the code here. I have a class named diamond. I have the methods that I should override, right? The equals method, right? Equals object, right? So cast this all right, so let's see. Now I'm not overriding the let me comment this out, this part. We're not worried about repeat. I'm not overriding the hash code, right? So I'm creating two objects. Pretty much just try to test the equals to see if those two objects are the same, right? So running this is pretty much is going to say they're different because blue and gray, right? Now let's print out the hash code. Pretty much just like now we didn't use hash yet, right? But whenever you use hash, it's going to use that hash code, right? But we could technically get the hash code, right? Dot hash code, right? And it should return what? Different hash code because these are two different objects, correct? Right, so those are the hash code, right? Now if I technically have the same, are they equals? It should return as they're equals, right? Because it's the same, but the problem is the hash code is not override. So that's why they're different, right? Because they're two different objects. So that's why this is going to create a problem in the hash table, right? Like we're looking for, it's going to slow down, right? Because in the hash, we technically want to see, hey, object is the same, right? Then we assume it's the same, right? Yeah, so that's pretty much what we're talking about here, right? If you have two objects which are equal but have different hash code, you lose. Make sense? The part of the contract here which is important is objects which are equals must have the same hash code, That's a contract. Understand now? And the reason because I say here you must do it in effective Java. The benefit pretty much, I think we seen it when we use in the hash, right, table. So how do you override then? How do you override the hash code? Effective Java, you must override hash code in every class that overrides equals. Failure to do so will result in a violation of the general contract, which will prevent your class from functioning properly in conjunction with all hash-based collections like hash map, hash set, and hash table. Let's look at example. What would happen if we override equals without overriding hash code and attempt to use a map? So say we have a class like this, okay, my class, and two objects of my class are equals. So let's see, my class, we have important field, and we said two object are equals if two important field is equals, right? Another field, equal field, another field, get equals, get another field. This is how you override hash code, right? And this is override the equals. So we said if this equals object return true, object equals no, return false, get class not equals to get class, return false. My class, this is just casting it. Other important field not equals to no, return false. Else if they're not equals, return false, right? Important field and other important field. Then the rest returns true. Now this, if you override the hash code, so prime equals 31, result equals to 1, results equals to, pretty much just you make, right, primes make a new hash code, right? Primes times result plus important field equals to null. If important field equals to null, return 0, right? Otherwise you just do important field dot hash code, add to that prime, so return a result. So you just implement your own hash code technically, right? And use hash code from the important field, right? When they're not equal to null. If they're equal to null, is 0. Now, if only equal is alright, then when you call my map.put key and the values, first we'll hash to some bucket, and when you call my map put, second it will hash to some other bucket, as they have different hash code. So although they are equals, as they don't hash to the same bucket, the map can't realize it, and both the same, them right, same in the map. So when you put, now you have to understand something about map. Map is different than the list that we learned so far. So what's good about map? So let's talk about bucket and map. Okay, let's talk about that real quick. Then you understand the statement that we just read. All right. So first talk about hashing technique first. So we have the word hash, right? So efficiency so far that we're looking at is what? Log n, right? With the binary, right? Search tree, right? Or with a tree structure. But if you're looking at the best is an array. Like an array when I want to look for a value at index 5. It's just jump to 5, I get the value. Key is 5, right? Returns value. And how long it take? 1. If I have the key, right? So I'm looking for employee ID 50704. So remember, 50704 in the list, if you look at n, it's going to iterate like 50704 or log n if you use BST, right? To find this employee, right? But we said we want to make it faster by mapping the key. So this is one bucket here, right? That we said we mod by 100. So we take the ID mod by 100. Boom, we get 04. That's the answer. Where the solution is. It's return the result. Make sense? And how long it takes? Just 1. Based on the hash technique, right? Use the function to return the location. Just like in the real world here, right? If you want to find a person, you just need the key, which is street address. Otherwise, in the whole wide world, how you gonna search for a person is too long, right? So that's the technique that we look at. Key, and then we get the values. So we can just go to the address, we find the person. It's faster than searching all the houses, compare is this a person in there. So that's hashing. So that's why the key is what? Person live in Springfield. Person live in Annandale. So the bucket is Springfield bucket. The bucket is now Annandale bucket. Make sense? So then we'll talk about the bucket, right? So if you look at this one talking about bucket here, right? Bucket is a collection of elements associated with a particular hash location. Right, so like now, we gonna see the problem with they may have 2 employees that has an ending with 01, right? When we will get hash function. So that's why we had a bucket of 01, bucket of 02, bucket of 03, bucket of 04. That makes sense? So that's why this is called bucket, right? Okay. Now this is why explaining if only equals is overridden, Then when you call map.put, right, you add the values to it. With the hash function, hash code, right, the address location, first we hash to some bucket, and when you call another again, it will hash to some other bucket. Because what hash codes are different. So when hash codes are different, it could jump into different bucket, even the objects are equals. So that's why you not having efficiency, right, for the hash. Although it is not necessary to override equals, if we override hash code, let's see what would happen in this particular case where we know that two objects of my class are equal. If their important field, if e is equal, but we do not override equals. So if we only override hash code, so we set new class A first, right? Second, new my class A second. If you only override hash code, then when you call mymap.put, it takes first calculates its hash code and store it in a given bucket. Then when you call put second, it should replace first with second as per the mapped documentation because they're equal. But the problem is they're not, right? Because the equal was not redefined. So when the map hashes second and iterates through the bucket looking if there's an object k such that second dot equals k is 2, it won't find. So meaning that you don't want to override just one, right? You want to override both. Make sense? Yeah. Like now, we technically want to override hash code, right? And how to override, you technically just create a new hash code for it. And so we override equals, we override hash code. So in this case, we look at color, right? Because our field is the color. Now they have the same hash code because we created, right? Then when we put this in the map, it's going to be in the same bucket because it's the same. Okay? All right. So this is something that we should know about hash code and override in the hash. Any question on that? All right, so we pretty much done with the hash concept here when I review this. So since we start to talk about hash, let me finish this up. So hashing is based on what hash functions. Hashing is just the technique, right, for ordering and accessing elements in a list, right, for a constant amount of time by you manipulating the key. And we have hash table, pretty much just the data structure used to store and retrieve elements using hashing. Like in this case, this is called hash table, hash function, and hashing technique is just the technique that we're talking about the whole thing here. So If you want to implement hash, so hashable interface, gonna be a hash method, which is a hash function. You're gonna create a mathematical model in this to manipulate the key to identify the location in the list. So this is when you add. So technically the same, like we add and we get, right? There are two of them. So when you add a new element, so we're going to call hash. Hash should return the location, like hash function. In this case, hash is the mod by 100, right? So if I give the ID 31300, so location should be 00 because remainder, right? So that's why I just go to that array location 00 and put the elements in, and then increment the number of elements in the list. That makes sense? And when we get the same, we just call hash is return location and return that location. So that's why it's only take one. Now we can see there's gonna be a problem we call collision. When the pretty much I have 50500, it's gonna be collision because we only have one. So that's why we have to create buckets, right? When it's happened to be the same location, we have to put in the same bucket. Pretty much now the time it takes is going to be smaller, right? But it's no longer one, right? But it's still iterate through the same bucket list. Makes sense? But it's still smaller than iterate through everything, right? Okay. Now there's so many techniques besides bucket. So like most likely they use bucket in the Java, right? So that's why we talk about bucket, because it's the better approach than linear probing. So linear probing is another technique. Like we were talking about bucket. Bucket pretty much just an image like this, right? This is the bucket, right? You just iterate to that. It's just like table now, right? Or you can use linked list to implement bucket too. Just create a list, right? Another linked list of array list, right? With the same O3, right? Now another approach we call, I mean, it's not the best one, but that could be done. We call linear probing. So what's linear probing? It's just like, okay, I said, I have 50500. I could just go to the next one and look for it, and could go to the next one and look for it. In case of add, this is empty, then I'm going to add it right there. So I can just add 50500 in the next available address. That's called linear probing. When you search the same thing, it's not matching, it's just linear probing. Oh, I found it. So pretty much just have one array, right? That's another way, okay? Now, this is showing you here, right? I try to do 77003, first free slot, that one, so it's gonna add into that one. The problem that you see is what for this approach. We cannot be sure that our element is in location, right? Because it's going to create a cluster. Like, what happens if I have key 05? Then that is no longer valid. It has to probe to another one again, right? So that's the problem, right? We must examine every array element starting with location that we hash until we find the matching elements. It's still better than from the beginning, but when it's clustered, it's not really efficient, right? We cannot stop looking when we reach an empty location because that location may represent an element that was previously removed. This problem illustrates that hash tables in the form that we have studied thus far are not the most effective data structure for implementing lists whose elements may be deleted. Right? What happens if it's deleted? We're going to keep searching throughout the list. So that's why they also have another techniques beside linear. They call clustering. The tendency of elements to become unevenly distributed in a hash table. I mean, this is the problem, right? It's going to be clustering. With many elements clustering around a single hash location, we can see that. Rehashing, resolving a collision by computing a new hash location from a hash function that manipulates the original location rather than the element's key. So besides linear, they have quadratic probing. Like instead of going to the next one, it's just going to add or search according to rehashing formula. Quadratics, just like hash value that you get, you plus or minus I square, and then moderate size. So I just the index, the location. So it could be jump into a quadratic, like different location. And also we have another technique we call random probing, pretty much just resolving a hash collision by generating the pseudo-random hash values in successive application of the rehash function. Just pretty much just create a new location randomly and just go and insert to it. Right. Those are beside linear. Now we have bucket, like we've seen that, which is the approach that we use in Java. And that's pretty much it for hashing techniques. Okay. So you should review that, right, for your final exam, right? So the PowerPoint, the chapter 10 pretty much just talk about sorting, searching. We were talking about that already, like log and search and log and sort. And then hash. Alright, so we pretty much done with the hashing. Any question on hashing? Now if I ask you about the contract, alright, why we need to override equals and hash code, now you understand how to explain that, right? And the test. Alright, so we're gonna look at, now we come back to look at we were learning how to construct a binary search tree and AVL trees already. What we need to look at is how we when we remove, right? What happened to it? And then we have the hashing chapter in 27 too, the one that we just mentioned. So since we talk about hashing, let me go through this chapter 27 real quick and let's finish hashing, then we don't have to worry about it again. Okay. And then we only have graph left. And if we have time, we could cover the rest right there. 2, 4, and red, black, and testing, which we will have time. According to our syllabus, we will finish that. And one chapter that I'd like to discuss is the web services. This is just extra, it's not on the syllabus. Okay, I mean, yeah, it's not on our, but we can look at that when we have more time. So let's talk about, finish up hashing in chapter 27. So it's technically big of 1, right? Time to search, insert, and delete an element using hashing. So we have been looking at using the binary search tree. It's going to be log n for a well-balanced search tree, which is AVL. So hashing based on the key and index, right? Map a key to an index, right? And we just reviewed the map already. Hash key and then index. So each entity contains 2 parts, key and values. We already seen that, like the dictionary. Now in Java collections we have util.map, java.util.map, which is an interface, right? We look at that already. And the concrete implementation are hash map, linked hash map, and tree map. Hash map is implemented using hashing. Link hash map using linked list, and tree map using red black trees. We talk about red black trees. How do you decide a hash function that produces an index from a key? We would like to decide a function that map its search key to a different index in the hash table, and this is called a perfect hash function. So when 2 or more keys are mapped to the same hash value, we call collision. We see that. And the solution to collision is what? Linear probe, quadratic probe, randomly, right? Probe, and what? Buckets, right? Buckets, array in array, right? Or chaining. Chain is pretty much like bucket. Chain pretty much is array and then linked list. So hash function and hash codes. A typically hash function first converts search key to an integer value called a hash code, then compresses its hash code into an index to the hash table. We talk about that again. Object, right? Class has a hash code method which returns an integer hash code. By default, the method returns the memory address for the object. The general contract for the hashcode method is follows. We talk about this, right? You should override the hashcode method whenever the equals method is overridden to ensure that 2 equal objects return the same hashcode. During the execution of a program, invoking the hashcode methods multiple times return the same integer, provided that the object data are not changed. Two unequal objects may have the same hash code, but you should implement the hashcode method to avoid too many such cases. That's going to be something that, right, an equal object may return hash code. Yeah, same hash code. So we're going to do that to, yeah, when we override, avoid that. So hash codes for the primitive types, like for search key type byte short int char, simply cast them to int. So two different search key of any one of these type will have different hash codes. For search key like float, use float to int bits key as the hash code. Like we were talking about this because they don't have hash code, right? They don't have hash code methods because they are primitive type. We cannot do dot hash code. Then we simply cast them to int. To make sure they all have different hash code. Now for the float, this is like the decimal, like the infinite, right? Float long. How do we do that? It's recommend you to use the wrapper class float to int. Just change it to int, right? Bits. So it's going to return an integer value whose bit representation is the same as the bit representation for the floating number f. That will solve the problem. So different search key of the float type will have different hash codes in this case. So how about long? Simply casting it to an int would not be a good choice because our keys that differ in only, that it's only differ in the first 32 bits and long is 64 bits, so it will be a problem, right? We have the same hash code. That's a problem. So to take the first 32 bit into consideration, we're going to divide the 64 bit into two halves and do the exclusive OR operation to combine the two halves. And this is called folding. So this is the example. So we get the first key and get the another half, right? So you shift, this is shift operator, right? So you get another half and then you do exclusive OR, then you get a hash code for the long. Okay, so this is just the right shift operator. Like for example, you have 10 10 you shift this into 2 bits, so it's going to shift to the right 2 times. Okay, like 1 0 will replace with, like, technically you can just cover this part and the rest is going to be the answer because you shift 2 times. So 10101 with O in front. Okay, so this is pretty much just what, when you shift 32 times, you pretty much just get the upper half of this 64 bits, right? Then we can do XOR and get a hash code. Like in this case, we get a hash code. Alright, so now we understand how to get a hash code, right? So for the object, we have to, by contract, override the hash code, right? To override the hash code. Why we have to do that? Then objects will return the same hash code if they are equals, right? Also, an equal object may have the same hash code. We don't want that to happen. And then we said hash code for primitive type. If they're not float and long, we just cast them to int. Right. For float, we use float to int bits. For long, we have to do shift right operators 32 times and do XOR, get the hash code. Now for double, so for double we first convert into a long by using double to long bits, and then perform the same folding, we call folding, right, after we convert. So that should take care of all the primitive type, right? How many primitive data type we have? 1, 2, 3, 4, 5. The int itself, right? 1, 2, 3, 4. And float, right? 5. Long, 6. Double, 7. And Boolean pretty much is not in this one, right? 8. Okay. How about hash code for strings? Right, and search keys are often strings. Again, key is the hash code, right? And if we use strings as a key, then how would we create a hash code for strings? So it's important to decide a good hash function for strings. An intuitive approach is to sum the Unicode of all the characters as a hash code for the string. This approach may work if two search keys in an application don't contain the same letters. So we know that all the characters has a Unicode, right? So it says sum them up. It will work if they don't contain the same letters, but it will produce a lot of collisions if the search key contains the same letters, like dot and dot, right? So that's collision, even they're not equals, because they return the same search key. A better approach is to generate a hash code that takes the position of characters into consideration. Also, right, we said, okay, we should take the location of the letters itself too. So this is looking at S at the character, right, at location, because char at returns the character at the specified index. So this is called polynomial hash code. Using Horner's rule for polynomial evaluation, the hash code can be calculated effectively as follows. So this pretty much is a sequence of the characters, right? So S0, S1, pretty much is the sequence of each characters. And B pretty much just some positive numbers. Now, when we have a long string, this will cause an overflow. Now, but arithmetic overflow is ignored in Java, so you should choose an appropriate value B. So this is pretty much a positive B, right? Some positive value. So if you choose an appropriate value to minimize collisions, and a good B is 31, 33, 37, 39, and 41. Okay. So this is related to when we override hash code, we call 31. we use that, right? So say the hash code is overridden using the polynomial hash code with b being 31 in the string class, right? So we already know string class in Java, they use 31 for the hash code. So this is pretty much just talk about hash function, right? Compressing hash codes. The hash code for a key can be a large integer that is out of the range for the hash table index. So you need to scale it down to fit in the index range. So assume the index for a hash table is between 0 and n-1. The most common way to scale an integer to between 0 and n-1 is to use the modulator n. To ensure that the indices are spread evenly, choose n to be a prime number greater than 2. Ideally, you should choose a prime number for n. However, it's time consuming to find a large prime number. So Java API has hash map, right? That n is set to a value of the power of 2. That's what they use. So when n is a value of the power of 2, so this is the hash code mod n is equivalent to hash code, and this is what bitwise operator like for the n by bit, right? And operate by bit with 1 alpha signs. So like it's the same as that n-1. Let's see example. Like if I have n equals to 4, alright, and my hash code is 11 mod 4, we get 3, right? Because 4, 11, 4 is 8, 3 is remainder, right? Now if you look at bitwise operators, hash code 11, 11 is 01011, right? Which is 1011 is 11, right? Now when you bitwise with 4 minus 1, this is 00, this is 3. When you do bit operator, 1 and 1 is 1, 1 and 1 is 1, the rest is 0. So we get 1, 1, which is 3 back. Right, the same thing as hashcode mod n. Now, we rather use what? Bitwise operator, because computer dealing with binary numbers instead of using modulators for efficiencies. So this will perform faster. It's much faster than use mod operator because it doesn't have to convert back and forth between binaries and decimals values. So the reason we want to do that, because again we said it takes time, right? So we can minimize by using this for the function to get the hash code function. So that's one way to scale down, right? And integer to between 0 and n-1. Now to ensure that the hashing is evenly distributed, a supplemental hash function is also used along with the primary hash function in the implementation of hash map. So this is called supplemental hash function. You pass H. So we have, these are bitwise operators again, right? This is XOR, right? And this is, so if we have two of them, we call right shift. Three of them we call unsighted right shift operations. This is our Java bitwise operators. And the reason we want to use bitwise because it's when you manipulate like this, is deal with the binary directly. It's much faster, right, than doing multiplication, division, and remainder operations manually. So we recommend you to replace all the multiplication, division, and remainder with the bitwise operators. And technically, multiplication is happening when you shift bit. Okay. And then when you shift bits to the left, you multiply by 2. If you look at, let's look at a sample a little bit. So that's why we recommend when you do multiply, just use bitwise operators to make more efficiency. Like for example, if I have number 2, right, in decimal, in binary it was number 2 again. 10, right? Correct? 0010, right? Now, if you look at, I want to multiply 2 by 2, what do we get? 4, right? But this one will cost a lot of CPU, okay? It's not efficient. Efficient code to multiply is this. In Java, you just shift bit to the left. Shift it to the left one time. This is giving you 4 in binary. See that? So, and we use bitwise operators again to help. Shift left is, this is shift left. So this is pretty much just a supplemental hashcode function that being used in HashMap. To replace the multiplication, division, and so on. Pretty much this is a hash function. When you decide a hash function, you should consider using bitwise operator instead. Okay? Because you have a chance to decide your own hash function. So we just talked about linear probing already. So we can go through this. That's handling the collision. We talked about quadratic probing. So we know the problem with linear probing is it can create cluster, right? So now for cluster, just allow the same area, right? So that's why solution using quadratics is will eliminating the clustering, right? So it's just use k plus j square mod n. Again, this is just in the term of showing us, right, the formula, but we recommend you to do what whenever you mod n, you replace with what bitwise operator, which is n minus 1 instead of mod n, because we already proved it's equivalent, right? Alright, so quadratic So let's look at the animations. So quadratic probing increasing the next index in the sequence by j square. Right. For example, we get what, 26, and it's 11. 26 mod 11. What do we get? 4. So we get to 4, but it seems like something already there because 4, right, itself. Then we say we use quadratics. Quadratic probe 2 times before finding an empty cell, right? So quadratic is what? J square. So what's j square? Let's look back. So it said linear probe look at a consecutive cell beginning at the index k, but quadratic probing, on the other hand, looks at the cell at indices plus j square, starting from what, j greater than or equal to 0. So the first one is going to probe to pretty much just what, 1, like itself, which is 0, and then 1, and then 4, right? So the sequence is going to be next one is going to look at is what, j squared, which is 1 square is what, 1, plus 4, that's why it's just jump to 5, right? And the next one is going to be 2 square, is it right? Which is what, 4, add to its index 4, which is 8, right? So it's jumped to 8, right? And if you keep going, j is going to keep increasing by 1, right? So after 8, where it's going to go? 3 square, right? 9 plus 4, 13, right? But since we don't have to go to 13 because we have an empty space, right? So that's a quadratic probing. Okay? This is going to eliminate the clustering for sure. We can see because it keeps jumping, right? So it's the same as linear, but it's just probing by the j square, right? It's going to have its own clustering problem called a secondary clustering. That is the entry that collide with an occupied entry use the same probe sequence, right? If it's using the same, it's going to be a secondary clustering. So in linear probing, it guarantees that an available cell can be found for insertion as long as the table is not full. That's true if it's keep going, right? However, there's no such guarantee for quadratic probing. There's no guarantee on that. Now let's look at double hashing. So it's another open addressing scheme that avoids the clustering problem. Is known as double hashing. So starting from the initial index k, both linear probing and quadratic probing, and an increment to k to define, add an increment to k, right? K is an index to define a search sequence. The increment is 1 for the linear probing and j squared for a quadratic probing. So these increments are independent of the keys. Double hashing uses a secondary hash function, like you hash again, right? So with another hash function, we call it hpalm, right? Key. On the keys to determine the increments to avoid the clustering problem. The whole thing here, but just to avoid clustering. This one we didn't talk about bucket, right? So that's why we use these techniques. So double hashing looks at the cell at the indices H prime key and then multiply by j and add to the index, right? Mod n for j greater than equal to 0. So that is k mod n, and the next one pretty much is k plus h prime key mod n and k plus 2, because j is going to be increment, right? 0, 1, 2, 3, and so on. So for example, let's the primary hash function h and secondary hash function h prime on a hash table of size 11. So h key equals to key mod 11, and now h prime key equals to it's going to come back to k, right? Because this depends on this, right? Key mod 7. So this is talk about size 11, right? Size 11. So where 7 is coming from? So k plus j times h prime key. Now h prime key is it seems like it's already decided that way, huh? But wonder. Now let's look at, if we want to search for 12, it's going to plug in, then we get 1, right? And then the hashing again with another hash table. So another hash function is set from key mod 7, 7 plus key mod 7. So it's going to get 2. And we said, suppose we already have this key in table. We now insert the element with key 12. Right, we have 12. The probe sequence for key 12 start at index 1, since its cell at index 1 is already occupied. So search the next, because 21, right? We have key index 1 already occupied. That one, right? So search the next cell at index 3. Because of this one, right? K plus j, which is technically in this case is to the hash key here when j is 1, so 2 plus 1 is 3, right? So it's going to go and search at index 3. Since the cell at index 3 is already occupied, search the next cell at index. So it's going to be the same. So it's going to do multiply by 2, right? 2 times 2 is 4 plus 1, so it's get at index 5. Now index 5 is empty. Then the elements 12 is now inserted at this cell. So that's pretty much like double hashing. That's another technique. So the indices of the probe sequence are as follow. Like if you look at, just keep plugging in this, right? We see 1, 3, 5. Next one pretty much just 3 times 2, right? 6 plus 1 according to this. So 7 and keep going, right? And mod n, right? And n is 11. So when it reach to 9, then it's get to 0 because of mod n. Alright, so this is just showing how the double hashing works. Now, like we said, those are the technique, right? So we have learned one more from this textbook, which is double hashing. So we also have another solution, which is separated chaining. We call implemented bucket using array list or linked list. Okay, we've seen this already. So how about load factor and rehashing? Load factor measures how full a hash table is. If the load factor is exceeded, increase the hash table size and reload the entries into a new larger hash table. Just like the factor when we were looking at hash linked hash map, right? They have a f factor 0.75. Same here, right? So it's going to rehash into a new bigger hash table. So we call rehashing. Now load factor represented by lambda. It's just to make sure how full a hash table is. So the ratio of the number of the elements to the size of the hash table, right? So n, small n denote the number of elements, and big N is the number of location in the hash table. So this is called load factor. So lambda is 0 when the hash table is empty, and lambda should return something like a percentage when you divide that between 0 and 1, right? So studies show that you should maintain the load factor between 50% to 90%. Keeping the load factor under a certain threshold is important for the performance of hashing. In hash map, the threshold 0.75 is used. So when it exceeds the threshold, you need to increase the hash table size and rehash all the entries in the map into a new larger hash table. You need to change the hash function since the hash table size has been changed. Whenever you rehash, you need to change the hash table and hash function, I mean, because hash table is changed. To reduce the likelihood of rehashing since it is costly, you should at least double the hash table size, even with, we lost the internet, huh? Sorry. So next chapter is the graphs, but let's come back to hash. Here, right? So to reduce the likelihood of rehashing since it's costly, you should at least double the hash table size. even with the periodic rehashing, hashing is an efficient implementation for map. Alright, so this is just showing you the bucket, right? And Shane, we know that already. So we come back and look at the using hashing, right? We implementing a map. Okay. So we start to look at implementation next class when we come back. Okay, for the map. All right.